Hello everyone, welcome back to learn the axially loaded member. In this lesson, we will study the local stability calculation of axially loaded compression members. First of all, let's study the concept of local stability of axially loaded compression members. The so-called local stability is defined as an ability of the plant elements made up of a steel member to resist its buckling failure before the overall instability of a member occurring. If a compression plant, such as the flange at the web of the I-shaped column, can't maintain its equilibrium state under a certain loading and develops a concave convex curved deformation out of its midplane before the occurrence of a global buckling, this phenomenon is called local buckling. Local stability of compressed plant elements on an axial compression member can be studied by reference to the elastic stability of an infinite plant having wings B and thickness T as shown in Figure 12. Assume that the four sides of the plant are simply supported and the compressive forces act on two supported sides having wings B. The critical stress of this plant is given by equation 4-8. In equation 4-8, mu is the Poisson's ratio of the steel, B to T is the wings to thickness ratio of the plant, K is the buckling coefficient, and E is Young's modulus of the material. Chi is the embedment coefficient or elastic restraint coefficient, and its value is generally greater than or equal to 1.0. As it can be seen from equation 4-8, when the boundary conditions of the plant and the material property are given, the critical stress of the plant is only controlled by the wings to thickness ratio of the plant. The above formula is derived for plants having four simply supported sides. If the boundary conditions of the plant change, the value of the buckling coefficient K will change as well. The specific value of the coefficient K depends on the constraints along the non-loaded edges of the plant. For example, as shown in Figure 13, for plants with four simply supported sides, the value of buckling coefficient K is equal to 4. For three sides simply supported and one side fixed plant, the value of buckling coefficient K is equal to 5.42. For plants simply supported on two opposite sides and fixed on the other two, the buckling coefficient K is equal to 6.97. The buckling coefficient of plants with three sides simply supported and one side free is 0.425, whereas the buckling coefficient for the plant with two opposite sides simply supported, one side fixed and the other side free is 1.277. The critical stress given by the above formula does not consider the influence of the material's plasticity. After considering the elastoplastic effect of the material, the critical stress of the plant can be further expressed by equation 4-9, where it is the ratio of tangent modulus to Young's modulus, which is called elastic modulus reduction coefficient. Since the local buckling critical stress of the plant is inversely proportional to the wings to thickness ratio of the plant, the maximum value of the wings to thickness ratio of the plant should be limited to ensure the plant has enough local stability capacity. For axially loaded compression members, the limit value of the wings to thickness ratio of the plant element is usually determined according to the equivalent stability criteria. This criteria requires the local buckling critical stress of the plant constituting the axial compression member equal to or larger than the overall stability critical stress of the column. Thus, no local buckling would occur before the overall instability happens. Next, let's take the most common S-section axially loaded compression member as an example to derive the winds to thickness ratio limit value for its flange at web. In an S-section member, the flange can be regarded as a uniform compression plant with 3 sides simply supported and 1 side free, whereas the web can be regarded as a uniform compression member with 4 sides simply supported. The limit value of the winds to thickness ratio of a flange and web can be derived according to the aforementioned equivalent stability criteria. The obtained results are given in equation 4-10 and equation 4-11. In these 2 equations, B refers to the free extended winds of the flange. Lambda refers to the larger slenderness ratio of the components around the 2 principal axes. The value of lambda should satisfy the following conditions. When lambda is smaller than 30, lambda should be equal to 30. When lambda is larger than 100, lambda should be equal to 100. Using the same method, we can get limit values of the winds to thickness ratio of other common cross-section axial compression members, which can refer to the corresponding design code. In this lesson, we have studied the calculation of the local stability of the plant in an axially loaded compression member. In the next lesson, we will learn the design methods of solid web axially loaded compression members. See you next time.